In this lecture, we will discuss the Kirchhoff's current law or the KCL. The Kirchhoff's laws are more comprehensive than the Ohm's law, and they are used for solving electrical networks which may not be readily solved with the help of Ohm's law. There are two types of Kirchhoff's laws, and these are particularly useful in determining the equivalent resistance of a complicated network of conductors and for calculating the currents flowing in the various conductors. The two Kirchhoff's laws are the Kirchhoff's current law, which is written in short as KCL, and the Kirchhoff's voltage law, which is also written in short as KVL. In this lecture, we will be discussing the Kirchhoff's current law or the KCL. The Kirchhoff's current law states that in any electrical network, the algebraic sum of the currents meeting at any point or node or junction is equal to 0. Note that here we are using the word algebraic sum. We are not using the term sum. So algebraic sum means that we are taking the sum of all the currents considering the sign of the currents. Or we can say that the total current leaving a node or a junction is equal to the total current entering that node or junction. In other words, we can say that the Kirchhoff's current law obeys the law of conservation of charge. This is true because there cannot be any accumulation or depletion of current at any junction of the network. So, the Kirchhoff's current law states that the algebraic sum of the currents at any node or junction will always be equal to 0. Now let us understand the Kirchhoff's current law with the help of an example. For this, let us consider the figure shown in the figure A. Here we find that there are few conductors which are meeting at the junction A. A is also known as node. So A is the node or junction, and there are few conductors which are meeting at this node or the junction. Also, we find that some of the conductors have currents which are leading to the point A, as we can see here that the current I1 is leading to point A, the current I4 is also leading to point A, and there are some other conductors which are leading away from point A. Here the current I2 is leading away from the point A, current I3 is also leaving away from point A, and the current I5 is also leaving away from point A. Now let us assume that the incoming currents be positive and the outgoing currents are negative. So we have assumed that the incoming currents will be treated as positive and the outgoing currents will be treated as negative. So if the incoming currents are positive, that means that the value of I1 will be positive because this is entering the node A. So this is the incoming current. This is also the incoming current. So the current I1 and I4 are positive. Now we find that I2, I3 and I5 are leaving the node, that is they are outgoing currents, and we have assumed that the outgoing current is negative. So the sign of I2 will be negative, sign of I3 will also be negative, and sign of I5 will also be negative. So we find that I1 is positive and I4 is positive because I1 and I4 are entering the node A, and I2, I3 and I5 are leaving the node A. So the sign of I2, I3 and I5 are negative. So we will add all these currents according to the sign of the currents. So this is that is we are taking the algebraic sum of the currents. So if we apply Kirchhoff's current law at this node A, then we can write that I1 plus minus I2 plus minus I3 plus I4 plus minus I5 is equal to 0, or I1 plus I4 minus I2 minus I3 minus I5 is equal to 0, or we can write I1 plus I4 is equal to I2 plus I3 plus I5. That is, the sum of the currents which are entering the junction is equal to the sum of the currents which are leaving the junction, or we can write that incoming currents is equal to outgoing currents. So we find that sum of the currents entering the node is equal to the sum of the currents leaving the node. Now let us take another circuit shown in the figure B. In figure B again we find that there are few conductors having the currents as shown by the arrow symbol. So if we apply Kirchhoff's current law at the node A to this circuit shown in the figure B, then we can write plus I1 plus I minus I1 minus I2 minus I3 minus I4 is equal to 0, because we have assumed that the current which enters the node, we have taken this current as positive, so these currents are going away from the node, so these currents will be negative. So if we take the algebraic sum of the currents at this node A, then we find that I plus minus I1 plus minus I2 plus minus I3 plus minus I4 is equal to 0, or we have I is equal to I1 plus I2 plus I3 plus I4. So we find that incoming current is equal to sum of outgoing currents. So mathematically we can express the Kirchhoff's current law as algebraic sum of all the currents is equal to 0 at a node or junction. That is, algebraic sum of the currents at a node or junction is equal to 0. So this is Kirchhoff's current law.